Hello everyone, welcome back to the Math Office. Today we're going to talk about biconditionals and definitions. Now, a biconditional statement is a statement that can be formed by joining a conditional statement with its converse if both of those statements are true. Let's look at an example here on the board. We have a conditional statement. If it is October 31st, then it is Halloween. And then we have its converse. If it is Halloween, then it's October 31st. To write a biconditional, we take the if and the then from each of these statements. Now, they both use the same parts. It is Halloween and it is October 31st. Take those two parts, remove the if and then combine them with the phrase if and only if. So our biconditional in this case is it is October 31st if and only if it is Halloween. Now, you could reverse those. You could say it is Halloween if and only if it is October 31st. The order does not matter. So that's how you write a biconditional given a conditional statement and its converse. Now let's take a look at how to reverse that process, how to break a biconditional down into a conditional and a converse. Here on the board we have a biconditional statement. Mr. Brenneman is your teacher if and only if you are taking geometry at New Tech. This is a true biconditional. Now we can break this down back into a conditional statement and its converse. Let's look at the two parts of the statement. If we remove the if and only if, the two parts of the statement is Mr. Brenneman is your teacher and you are taking geometry at New Tech. Now we can use these two parts and turn them back into a conditional statement and its converse. So our conditional statement might be, if Mr. Brenneman is your teacher, then you are taking geometry at New Tech. The converse of that would be, if you are taking geometry at New Tech, then Mr. Brenneman is your teacher. So there we have a quick example of how to take a biconditional and break it down into a conditional statement and its converse. And they're both true statements as well. Now let's take a look at good definitions. What is a good definition? Here's an example of a definition on the board. A right angle is an angle that measures 90 degrees. Now the question is this a good definition? The way to tell is to see whether or not this definition is reversible. In other words, you take the two parts of the statement and you switch them around. If it's still true, then it's reversible and a good definition. So let's take a look at this. Let's reverse it. An angle that measures 90 degrees is a right angle. This is true. So we have a good definition here. Now, when we have a good definition, we can rewrite it as a biconditional. So here's what it would look like. An angle is a right angle if and only if it measures 90 degrees. So when we have a good definition, we can rewrite it as a biconditional. Let's take a look at an example of a definition that's not a good definition, that's not reversible. We have a definition on our board here. A square is a figure with four right angles. Now, so far, this is a true statement. A square certainly does have four right angles. But let's reverse it and see if it's still true. So the reverse of this is a figure with four right angles is a square. Now, that's not necessarily true. You could have a rectangle, which is not a square, and that would still have four right angles. So this is not a good definition because the reverse is not true. So we can't rewrite it as a biconditional. All we say is that this definition is not reversible. All right, well that's all the time we have for the Math Office today. Thanks for stopping by, and I'll see you again.